Today we're going to cover bending and flexure. Quick review of what everything means. So flexure is used to determine the normal stress in a straight member, or a beam typically, that has moment applied perpendicular to its axis. So the equation is sigma max equals mc divided by I. So sigma max is our max normal stress, m is the internal resultant moment, I is the moment of inertia, and c is the perpendicular distance from the neutral axis to a point furthest away. So you'll kind of understand what all of these mean once we do an example. But another way to represent it, the equation is m times y divided by I. So just to kind of understand what everything means from this equation is, if you have this straight beam and you apply a moment on the end, you will end up squeezing this beam, right? So the upper region becomes compressed and the lower region is stressed, so it's in tension, or stretched, so it's in tension. I guess you can visualize this if you grab a ruler and bend both of the ends. The top portion will curve in like this and the bottom will stretch out like that. So another thing is, imagine like this is the end of your beam and you're applying this moment. You're applying all of this force on this top portion, so this becomes compressed, and then this force here is leaving outward, so you have tension here. Now, the maximum compression and tension, they will always occur at the edges of your beam, whereas in the middle, that will be the lowest compression and tension, or the lowest stress. So in this example, they want us to determine the absolute maximum bending stress in the beam and the bending stress at point B. So we have this beam, they've given us a bending moment diagram and the cross section if we were to look at the side view of this beam. So what do we know? Based on this bending moment diagram, in section A, if we were to cut it, our maximum internal moment is 22.5. And we can deduce that because at 3 meters we're at 22.5, and it's the peak of our parabola. So we know m, and this m we can directly plug into our equation. Now typically they won't give you m. You will end up having to cut the beam and solve for the internal moment just like you would previously, which we've done so many times. But in this problem we don't have to solve for it. But what we don't know is the moment of inertia, and this is important because it goes back to the parallel axis theorem and all the way back to exam 2. So, refresher. I rectangle equals 1/12 base times height cubed. I total of a composite body is I rectangle plus AD squared. So here I choose to reference everything from the bottom of my body, and I have two identical segments, these two rectangles. So I start with 1/12 the base, 250, times the height, 20 millimeters cubed, plus the area, so 250 times 20, times d squared. Now, remember what d squared is. D squared is the difference between your neutral axis and the center of gravity of your body. So here, the neutral axis from the bottom to the axis is 170 millimeters. And then the center of gravity of this rectangle is halfway up. So halfway up is just 10 millimeters. So I have 170 minus 10. So this gives me the area moment of inertia just for this rectangle. And if I want to get it for both, I just multiply by 2. Now I look at the long rectangle here. 1/12 base, 20 times the height, which is 300 cubed, plus the area, 20 times 300, times d squared. Now once again, d squared, we start from the bottom, we go to the neutral axis, that's 170 millimeters, minus the distance to the center of gravity of this rectangle, and it just so happens that the center of gravity of this rectangle is also 170 millimeters, so this portion cancels out, it just becomes 0. And we end up with 4.5 times 10 to the negative 5th meters to the 4th. So now to find the overall moment of inertia for the entire body, we just combine those three segments. So 2 times this segment, because we have it twice, plus this segment, and we get 3.01 times 10 to the negative fourth meters to the fourth. Okay, that was the hard part. So now we know M, we know I, and I'm going to show you what C is, so we can find our maximum stress. So for M, I plug in 22.5. For I plug in what I solved. For C is the perpendicular distance from the neutral axis, so this is our neutral axis, to a point farthest away from the neutral axis. So the point farthest away from the neutral axis is the top of the beam or the bottom of the beam. Because it's symmetrical, both distance, either upward or downward, is going to be 170 millimeters. So I plug that in and I end up with 12.7 megapascals. Now, the second part asks us for the normal stress at point B. So once again, I plug in 22.5, I plug in the I that I solved, but what is Y? Y now is the distance from the neutral axis to the designated point, which in this case is B, so it's just 150 millimeters. And that gives me that the normal stress at point B is 11.2 megapascals.